Before we dive in, please remember that this video is for informational and educational purposes only. The financial figures and examples discussed are based on industry reports and case studies, but they do not constitute financial advice. Always consult with a qualified professional before making significant business decisions. Imagine a brand new state-of-the-art gym. It has 1,000 treadmills, 1,000 weight benches, an Olympic-sized swimming pool, everything you could possibly want. But here's the insane catch. Only 10 people are allowed inside at any given time. The other 990 treadmills? They just sit there, plugged in, humming away, costing a fortune in electricity and maintenance. The massive pool? Perfectly clean, perfectly heated, and perfectly empty. It sounds completely absurd, right? A colossal waste of money and resources. Well, this exact scenario is playing out right now, in real time, inside thousands of American companies. Not with gym equipment, but with something infinitely more expensive and critical to their survival: their computing power. And this hidden waste is costing them and potentially you a fortune. In this video, I'm going to pull back the curtain on one of the biggest, yet most overlooked financial drains in modern business. And more importantly, I'm going to reveal the single brilliantly simple strategy that the smartest companies in the world are using to plug that drain and save millions, sometimes tens of millions of dollars a year. It's a concept called resource pooling. And no, you do not need to be a Silicon Valley engineer to understand it. I'm going to break it down in plain English using real-world examples you see every day. By the end of this presentation, you will understand exactly what this powerful trick is, how it works, and how the core principle behind it can change the way you think about efficiency and cost no matter what industry you're in. This is the secret hiding in plain sight on the balance sheets of America's most successful companies. To really grasp the genius of resource pooling, you first have to understand the old broken way of doing things. Let's travel back in time just a decade or two. If you were a company, say an e-commerce store, and you needed a website, you had to buy your own computer servers. These are the powerful machines that store your website's data and serve it up to visitors. You'd buy these big, expensive metal boxes and you'd have to put them somewhere. This meant you either had to build your own special air-conditioned room, a data center, or rent space in one. This was your own private digital gym. And just like our absurd gym example, you faced a critical money-wasting dilemma. The question was always, how many servers do you buy? Let's say on an average Tuesday, your website gets about 1,000 visitors an hour. A couple of servers can handle that, no problem. But what about Black Friday? On Black Friday, you don't get 1,000 visitors an hour. You get 100,000. If your two little servers try to handle that massive spike in traffic, they will instantly crash and burn. Your website goes down, your customers get angry, and you lose out on the biggest sales day of the year. It's a total disaster. So what did companies do? They had to plan for the absolute worst-case scenario. They had to build their infrastructure not for the average Tuesday, but for the Black Friday tsunami. This meant instead of buying 2 servers, they had to buy 200. They had to build a data center with enough power, enough cooling, and enough security to run those 200 servers at full blast. And here is the soul-crushing, money-hemorrhaging problem. Black Friday only happens once a year. For the other 364 days, 198 of those expensive servers would just sit there, idle. They're not doing anything, but you are still paying for them. You're paying the electricity bill to keep them running. You're paying the massive air conditioning bill to keep them from overheating. You're paying the salaries of the IT staff to maintain them. You are paying for a Super Bowl stadium-sized capacity every single day, even when you only have a high school team's worth of traffic. This practice has a technical name: over-provisioning. And it was the standard way of doing business for decades. It was a terrible, inefficient model, but there was no other choice. Let me give you an even more extreme American example. A major tax filing website. Think about their traffic pattern. From January to April 15th, their website is one of the busiest places on the entire internet. Millions of Americans are logging on, filling out their forms and hitting submit at the last minute. The demand is astronomical. They need a digital infrastructure more powerful than most small countries. But what happens on April 16th? It becomes a ghost town. The traffic plummets by 99%. Yet, in the old world, that company would have to own and pay for that massive April 15th level infrastructure all year long. It's like owning a fleet of 1,000 snowplows in Miami, just in case there's a freak blizzard once a century. The cost is staggering. You are paying for peak capacity 100% of the time, when you only use that peak capacity for maybe 1% of the time. Then, about 15 years ago, a new idea came along that started to change the game: cloud computing. Companies like Amazon with its Amazon Web Services, or AWS, came along and made a revolutionary offer. They said, hey, instead of buying all those expensive servers and building your own data center, why don't you just rent them from us? We have a warehouse the size of a dozen football fields, filled with hundreds of thousands of servers. Just tell us how many you need and for how long, and you can use ours. Pay as you go. This was a massive leap forward. Suddenly, our tax filing company didn't have to buy a mountain of hardware anymore. They could just rent a huge number of servers from AWS for 4 months, and then on April 16th they could just turn them off. Stop paying for them. This saved them a fortune in hardware and maintenance costs. It was a game changer. Felt like the ultimate solution. But it wasn't. Because even with the cloud, most companies were still trapped in the old way of thinking. They were still renting their own private, isolated slice of the cloud. They were renting their own private gym, even if it was inside a bigger building. And that gym still sat empty most of the time. The real revolution, the trick that unlocked not just thousands but millions of dollars in savings, was yet to come. The cloud providers realized the secret wasn't just about renting equipment. It was about sharing it. And that, right there, is the deceptively simple, world-changing idea behind resource pooling. Imagine trying to build a city where every single family has to build their own power plant, their own water tower, and their own sewage treatment facility. It would be absurdly expensive, ridiculously inefficient, and an absolute nightmare to manage. Most of the time, that private power plant would be sitting idle, and that water tower would be mostly empty, but you'd still have to pay to build and maintain the whole thing just for those rare moments you need it at full capacity. For decades, this is exactly how the world of business computing worked. Every company built its own digital power plant, its own data water tower. They were called server rooms or data centers, and they were bleeding money. Resource pooling changed all of that. It's the digital equivalent of building one massive, hyper-efficient power plant for the entire city. Instead of every company owning their own physical servers, a cloud provider like Amazon, Google, or Microsoft builds a colossal data center. We're talking about buildings the size of multiple football fields, packed to the rafters with hundreds of thousands of servers. This is the pool. It's a vast, shared ocean of computing power, memory, storage, and network bandwidth. Now a company, let's call them Innovate Corp, doesn't have to go out and buy a server. They just connect to this giant pool and draw out exactly what they need when they need it. It's a model known as multi-tenancy. Think of it like a giant, ultra-modern apartment building. The cloud provider builds and maintains the foundation, the structure, the plumbing, the electrical grid, all the expensive, complex infrastructure. Innovate Corp, the tenant, doesn't have to worry about any of that. They just rent an apartment, a virtual server. And here's the crucial part. That apartment is completely private and secure. Your neighbor can't see into your living room, and you can't see into theirs. This is where the magic of virtualization comes in. Using a sophisticated layer of software called a hypervisor, a single powerful physical server can be sliced up into dozens of smaller, completely isolated virtual machines. Each virtual machine acts like its own independent computer, with its own operating system and applications. Innovate Corp gets one of these virtual machines, and another company, NextGen Solutions, gets another one, both running on the exact same piece of physical hardware. But to them it's invisible. They have no idea they're sharing. The hypervisor acts like an impenetrable wall between them, managing and allocating the physical resources, the processor time, the memory, so that no tenant can interfere with another. It's like a bank vault. The physical server is the giant, reinforced concrete vault. The virtual machines are the individual lock-safe deposit boxes inside. You have the only key to your box. The bank, the cloud provider, ensures that the integrity of every single box is absolute. This logical isolation is the bedrock of trust in the cloud. Now, this is clever from a technical standpoint, but the real genius, the part that saves US companies millions, is the economic model it unlocks. It's all about smoothing out the peaks and valleys of demand. Let's go back to the old way for a second. Before the cloud, Innovate Corp had to plan for their absolute peak traffic. Let's say they run an e-commerce site. They have to buy enough servers to handle the insane rush of Black Friday. But what about the other 364 days of the year? What about at 3 in the morning on a Tuesday in May? All of that expensive hardware, all of those servers they bought for that one massive peak, are just sitting there humming away, consuming electricity, taking up space, and doing virtually nothing. Studies showed that, on average, most company-owned servers were only being utilized at about 5 to 15% of their total capacity. It was an epidemic of waste. Resource pooling solves this by playing the odds on a global scale. The cloud provider isn't just serving Innovate Corp. They're serving thousands or even millions of customers from that same giant pool of resources. And all of these customers have different demand patterns. Think about it. Innovate Corp, the US-based e-commerce site, is slammed with traffic during daytime hours in North America, peaking in November and December. But sitting right next to them on that same physical hardware could be a financial analytics company based in London. Their peak is 5 to 8 hours earlier when the US is still asleep. And next to them could be a mobile gaming company whose traffic spikes in the evenings and on weekends, when both the e-commerce and finance companies are relatively quiet. And next to them could be a big data processing job for a research university that's designed to run only overnight, soaking up any available spare capacity. The cloud provider looks at this entire mix of customers and sees something beautiful. The chaotic, spiky, unpredictable demand of any single customer gets smoothed out. When you combine thousands of these different demand curves, you get one massive, relatively stable and predictable line. The peak of one customer cancels out the trough of another. This is a powerful statistical principle called multiplexing. It means the cloud provider can run their servers at incredibly high utilization rates, not 15%, but 70, 80, even 90% around the clock. This extreme efficiency creates massive economies of scale. First, there's the purchasing power. When you're a company like Microsoft or Amazon, you don't just buy a server, you buy them by the tens of thousands. You negotiate directly with manufacturers to get custom-designed hardware at a fraction of the price anyone else could. You build your own power substations to get electricity at wholesale rates. You can afford to locate your data centers in places with the cheapest power and cooling. No individual company can compete with that. Second, it completely transforms a company's financial model. The old way meant massive upfront capital expenditures or CapEx. Innovate Corp had to spend, say, $1 million on servers before they even made their first dollar of revenue. It was a huge, risky bet. With the cloud, that $1 million capital expense is gone. It's replaced by a monthly, operational expense or OpEx. You pay for what you use like a utility bill. This lowers the barrier to entry for startups and allows established companies to shift their resources from buying tin to hiring engineers and building better products. So, when we say resource pooling saves millions, it's not an exaggeration. It's the direct result of eliminating waste, leveraging global demand, and achieving a scale of operations that was previously unimaginable. It's the difference between every family building their own personal, inefficient power plant and an entire city plugging into a single, optimized, and unbelievably powerful grid. This shared infrastructure model is the foundation. But what happens when your needs change in an instant? What happens when your app gets featured on the news and your traffic doesn't just double? It multiplies by 1,000 in the span of 5 minutes. Simply having access to a big pool of resources isn't enough. You need to be able to dive into that pool and grab more, or release it back at a moment's notice. This ability, this incredible agility to grow and shrink on demand, is known as rapid elasticity. And how the cloud achieves that is the next layer of this multi-million-dollar secret. So, how does the cloud build this seemingly infinite pool of resources? How does it give companies like Netflix or your favorite online store the power to summon the strength of 1,000 computers in a blink of an eye? The answer isn't some brand new type of futuristic hardware. The secret, the absolute cornerstone of cloud computing, is a concept called virtualization. And to understand it, we first have to appreciate the colossal money-burning problem it solved. Let's imagine a classic American business, we'll call them Freedom Fireworks. A company that sells fireworks online. Their business is, as you can imagine, highly seasonal. For 10 months of the year, their website gets a little bit of traffic. But from May to July, it's an absolute madhouse. In the old days, say the early 2000s, how would Freedom Fireworks prepare for the 4th of July rush? Well, around February, their tech team would have a panic meeting. They'd look at last year's sales, try to guess this year's growth, and then make a very, very expensive bet. They'd have to physically buy computer servers. Not one or two, maybe 20, 50, even 100 new machines. These are big, powerful, expensive boxes of metal and silicon. They'd place the order, spending hundreds of thousands of dollars of the company's capital. Then they wait. Weeks, maybe months later, these servers arrive on giant pallets. A team of engineers has to unbox them, haul them into a freezing cold server room, physically bolt them into racks, and then meticulously wire everything up, power, networking, all of it. After that, they spend weeks installing operating systems, software, and security patches. It is a slow, expensive, labor-intensive process. And if they're lucky, they get it all done just in time for the first sparkler sale in May. The 4th of July comes and goes. The website handles the massive surge of traffic. Success. But what happens on July 5th? The traffic plummets back to normal. But Freedom Fireworks is now stuck. They own 100 powerful servers that are now sitting there, mostly idle, doing almost nothing. But they're not free. They are still consuming enormous amounts of electricity. They're still generating heat, requiring expensive air conditioning to keep the room from melting down. They're still taking up expensive real estate, and they still need people to maintain and patch them. For the next 10 months, the company is burning cash on a mountain of hardware they don't need. It's like buying a 500-seat Boeing 747 just to fly 2 passengers from Chicago to Omaha every day. It's an incredible waste of money. This was the reality for thousands of US companies. They were forced to build for their absolute peak demand, a peak that might only last for a few hours or a few days a year. The rest of the time, their investment was just depreciating in a cold, loud room. This is the problem that virtualization completely obliterated. Cloud providers like Amazon, Microsoft, and Google looked at this situation and realized the problem wasn't the servers themselves. The problem was that one company was tied to one physical machine. Their genius was to find a way to break that link. Here's the analogy that makes it all click. Think of a single powerful physical server in a data center as a giant empty warehouse. In the old model, Freedom Fireworks had to rent the entire warehouse, even if they only needed to store one small box inside. Virtualization is like hiring a master architect to come into that empty warehouse and build dozens of secure, separate, soundproof apartments inside it. Each apartment has its own walls, its own door, its own utilities, electricity, plumbing, everything. From the inside, each apartment feels like its own standalone building. You have no idea that you're sharing the same foundation and roof with dozens of other tenants. In the world of computing, this master architect is a special piece of software called a hypervisor. The physical server is the warehouse, and the individual apartments it creates are called virtual machines, or VMs. A single beastly physical server can be sliced and diced by the hypervisor into 10, 20, even 100 smaller independent virtual machines. Each VM gets its own dedicated slice of the server's processing power, its own chunk of memory, its own storage space, and its own virtual network connection. It runs its own operating system. For all intents and purposes, to the software running inside it, a virtual machine is indistinguishable from a real physical computer. Now, picture what a cloud provider does. They don't just have one warehouse. They have data centers the size of shopping malls, filled with hundreds of thousands of these warehouses, these physical servers. And on every single one, they install a hypervisor. Suddenly, they don't have 100,000 physical servers. They have millions upon millions of rentable apartments, virtual machines of all shapes and sizes, all ready to go. This is the origin of the resource pool. The pool isn't a magical cloud. It's a very real, colossal inventory of pre-built virtual machines, carved out of physical hardware and managed by hypervisors. So let's go back to Freedom Fireworks, but this time in the modern cloud era. It's February. There are no panic meetings. There are no massive purchase orders. They don't buy a single piece of hardware. They continue running their small day-to-day website on maybe 2 or 3 small virtual machines, paying a few bucks an hour. Now it's late June. The traffic starts to build. Their system, which they've configured beforehand, automatically sends a signal to the cloud provider. The signal says, "Hey, we're getting busy. We need 20 more of those medium-sized apartments right now." The cloud provider's hypervisor, the master architect, doesn't need to build anything new. It just looks at its vast inventory of available apartments across all its warehouses and instantly assigns 20 of them to Freedom Fireworks. Within seconds, those 20 new virtual machines are online, connected to the Firework website, and helping to handle the customer load. On July 3rd, as the real fireworks begin, the traffic goes vertical. The system sends another signal. This is it. We need 100 more of the large apartments. And we need them 5 minutes ago. The hypervisor obliges instantly. 100 more VMs are allocated from the pool and thrown into the fight. The website runs flawlessly. The sale is a massive success. But here's the multi-million-dollar moment. It's July 5th. The traffic is gone. The system sends one last signal. All clear. We're done. Release all those extra apartments. And just like that, the 120 extra virtual machines they were using are instantly returned to the cloud provider's pool. And the moment they are returned, Freedom Fireworks stops paying for them. Not at the end of the day, not at the end of the hour. They stop paying for them that very second. The financial difference is staggering. Instead of a massive upfront capital expense of $500,000 for physical servers that sit idle most of the year, they paid a much smaller operational expense, maybe a few $1,000s, for the exact amount of computing power they needed precisely when they needed it and not a second longer. They turned a massive capital investment into a predictable, pay-as-you-go utility, just like their electricity bill. And here's the final brilliant piece of the trick, the reason cloud providers can offer this so cheaply. It's a concept called multi-tenancy. Remember our warehouse full of apartments? Freedom Fireworks was just one tenant. In the apartment right next door could be a tax preparation company, whose busiest season is March and April. In another, a major news organization that gets a traffic spike whenever a big story breaks. The cloud provider is the ultimate landlord. When Freedom Fireworks releases its 120 VMs on July 5th, the hypervisor doesn't let that underlying physical hardware sit idle. It immediately rents that same capacity to another company hitting its own peak. By constantly shuffling and reallocating resources among thousands of different customers with different peak times, the cloud provider can keep its physical servers utilized at an incredibly high rate. This extreme efficiency drives their costs down, and they pass those savings on to the customer. It's the ultimate win-win. This is the engine of the cloud. This ability to abstract a physical machine into dozens of virtual ones is what creates the pool. It's what enables the elasticity, and it's what saves American companies not just millions, but billions of dollars a year. But this whole system, this global network of virtual apartments, instantly available for rent, would be useless without a key. A universal key that lets any company unlock this power, anytime from anywhere on Earth without ever talking to a human. And that key isn't made of metal. It's made of code. That code is the secret language of the cloud. It's a universal translator that allows any application, from any company, anywhere in the world, to speak directly to the massive humming brain of the data center. It's called an API, an application programming interface. Now, that sounds technical and boring, but an API is one of the most revolutionary ideas of the 21st century. And you can understand it with a simple analogy. Imagine you're in a restaurant. You, the customer, want food. The kitchen in the back has all the raw ingredients and the chefs to cook it. But you can't just walk into the kitchen and start grabbing ingredients. It would be chaos. You don't know the recipes, you don't know where anything is, and you'd get in the way of the chefs. You need an intermediary. You need a waiter. The waiter is the API. You don't need to know how to cook the steak. You just need to know how to read the menu and tell the waiter, "I'll have the New York strip, medium rare." The waiter takes your request, translates it into a language the kitchen understands, a kitchen ticket, and gives it to the chefs. The chefs do their complex work, and the waiter brings the finished product back to you. The API works exactly the same way. A company like Airbnb doesn't need to know how to build a server or configure a network switch inside an Amazon data center. They just need to use Amazon's API, the digital waiter, and say, "I need a virtual server with this much memory and this much processing power." The API takes that request, translates it into instructions for the giant automated kitchen that is the data center, and in seconds a virtual server is provisioned and delivered back to Airbnb, ready to use. This is the self-service magic that makes resource pooling possible on a global scale. Let's go back to our giant apartment building. The API is the building's automated, digital concierge. Before this, if you wanted to rent an apartment, you'd have to find a broker, fill out paperwork, wait for a credit check, sign a lease. It was a slow, manual, human-driven process. The cloud's API is a concierge that works at the speed of light and speaks every language. A developer at a small startup in Ohio can write a few lines of code that essentially tell the digital concierge, "I need a studio apartment with a view for the next 2 hours to run a quick test." And bam, the request is received. A vacant apartment is instantly allocated from the enormous pool. The digital keys are handed over, and the startup is billed only for the 2 hours it used. When they're done, they send another API call. "I'm checking out." The apartment is instantly wiped clean and returned to the pool, available for the next tenant, who might be a massive bank in New York needing to process end-of-day transactions. This wasn't just an improvement, it was a complete paradigm shift. To understand how profound this change was, you have to remember what it replaced. Picture a developer, let's call her Sarah, working at a promising tech company back in 2004. She has a brilliant idea for a new feature that could triple their user engagement. But to build it, she needs a new server. So she fills out a multi-page procurement form. She submits it to her manager, who has to approve it. Then it goes to the director, who also has to sign off. Then it lands in the finance department's inbox for budget approval. A week later, it finally gets to the IT purchasing department. They spend a few days getting quotes from Dell and HP. They place the order. The server itself takes 3 to 4 weeks to be built and shipped. When the giant cardboard box finally arrives, the IT operations team has to schedule time to unbox it, physically carry it into the cold server room, bolt it into a metal rack, and then begin the painstaking process of connecting power cables, network cables, and installing the operating system and all the necessary software. From Sarah's brilliant idea to having a server she could actually use, we're talking 6 to 8 weeks. Minimum. An eternity in the tech world. By the time her server was ready, a competitor might have already launched a similar feature. The opportunity could be lost forever. Now fast forward to today. A developer just like Sarah has an idea. She opens her laptop. She logs into her company's Amazon Web Services account. She can either click a few buttons on a web page, or more likely, she'll write a simple script. A few lines of code that use the AWS API to define the exact server she needs. She hits enter. The API call flashes across the internet to a data center in Virginia. The automated systems receive the request. They check the massive pool of available computing resources. They carve out a virtual slice, configure it exactly as she requested, and assign it an address. The time elapsed? About 30 seconds. She went from an idea to a fully functional, globally accessible server in less time than it takes to make a cup of coffee. This is not an exaggeration. This is the daily reality for millions of developers across the United States. This is the power of the API combined with resource pooling. It transformed the act of acquiring computing power from a slow, capital-intensive physical process into an on-demand, instantaneous, operational expense. It's like going from building your own power plant to just plugging a lamp into a wall socket. And this is where US companies started saving not just thousands but millions and even billions of dollars. First, the obvious: labor costs. The army of people needed to manage procurement, racking, and stacking physical servers was drastically reduced. Developers were empowered to get the resources they needed themselves, making them exponentially more productive. But the real savings, the game-changing money, came from destroying the concept of wasteful over-provisioning. In the old world, a company had to buy servers to handle their absolute peak demand. Think of an e-commerce site like Macy's. Their website traffic on Black Friday is maybe 50 times higher than on a random Tuesday in May. But they had to own and operate enough servers all year long to handle that massive once-a-year Black Friday spike. For the other 364 days of the year, 98% of that incredibly expensive hardware sat there, humming away, consuming power, generating heat, and doing almost nothing. It was like a taxi company being forced to own enough cars to handle New Year's Eve every single day of the year. The waste was astronomical. With the cloud's resource pool and its API key, this problem vanished. Now Macy's can run a small baseline number of servers for that Tuesday in May. But as the Black Friday rush begins, their monitoring systems can automatically make API calls to request more servers. 100 more. 1,000 more. 10,000 more. The cloud provides them instantly from the pool. The website handles the massive load flawlessly. Then, as the rush subsides, automated API calls are made to release those servers, sending them back into the pool. Macy's pays for that massive capacity only for the few hours they actually need it. This ability to expand and contract on demand is called elasticity, and it's the single biggest economic benefit of the cloud. It allows companies to perfectly match their resources to their needs, eliminating waste and converting massive capital expenditures into lean, predictable operating costs. So now we have the complete picture: a colossal shared pool of resources, and a universal self-service key made of code that lets anyone access it instantly. Seems like the perfect system, but it raises a terrifyingly important question. If Netflix and a brand new gaming startup are both renting apartments in the same building, if their data and applications are running on the very same physical machines, what stops one from seeing the other's data? How do you ensure that the walls between these virtual apartments are 100% soundproof and absolutely unbreakable? Because if you can't guarantee that, the entire model of shared resources falls apart. The solution to that problem is arguably the most ingenious piece of the entire cloud computing puzzle. It's a concept called virtualization, and it's managed by a piece of software so critical, so fundamental to the cloud, that without it, none of this would exist. This software is called a hypervisor. Now that word sounds complex, like something out of a science fiction movie, but the idea behind it is pure elegance. Let's go back to our apartment building. We established that simple drywall isn't enough. You can't just divide a building into rooms and hope for the best. The hypervisor is the architect who came in and said, "Forget drywall. We're going to give every single tenant their own pocket universe." Imagine you rent apartment 7B. When you walk in, it's not just a room. It's an entire self-contained replica of the entire building, just for you. It has its own private generator, its own private water supply, its own private foundation. From your perspective, inside apartment 7B, you are the only person in the universe. You have no idea that apartment 7C even exists, let alone that its tenant is blasting music. You can't hear them, you can't affect them, and most importantly, they can't affect you. The hypervisor is the technology that creates and manages these individual pocket universes for every single tenant, all while running them on the foundation of one single physical building. So how does it do this in the real world of computing? A physical server, the kind you can actually touch, is the building. It has real, tangible hardware, processors or CPUs, which are the brains, memory or RAM, which is its short-term workspace, and storage like a hard drive for long-term data. Before virtualization became mainstream, if a company needed to run an application, say their company email system, they would buy a whole physical server just for that one task. Then, if they needed a database, they'd buy another, completely separate physical server, and another for their website. You can see how this gets expensive fast. Most of the time, these servers were barely breaking a sweat, using maybe 5 or 10% of their total power, but you had to pay for 100% of it, not to mention the electricity to run it and the air conditioning to cool it. The hypervisor changed everything. It's a thin layer of software that gets installed directly onto the physical hardware, onto the bare metal of the server. It takes control of all the physical resources, every bit of processing power, every byte of memory, every inch of storage. Then it does something that feels like magic. It carves up these physical resources and uses them to build completely fake, simulated computers inside the real one. These are called virtual machines, or VMs. Each virtual machine is a complete, self-contained software package that thinks it's a real physical computer. The hypervisor presents a fake set of hardware to each VM. So, virtual machine A is told, here is your very own processor, here is your own 8 GB of memory, and here is your own 100 GB hard drive. Meanwhile, it tells virtual machine B, and here is your very own processor, your own 16 GB of memory, and your own 500 GB hard drive. But here's the trick, the grand illusion. There's only one real processor. There's only one real pool of memory. The hypervisor is like an impossibly fast, brilliant translator standing between the fake computers and the real hardware. When VMA needs to calculate something, it sends a request to its fake processor. The hypervisor intercepts that request in a fraction of a millisecond and says, "Okay, I'll run that calculation on the real processor for you." It gets the answer and hands it back to VMA, which is none the wiser. It has no idea it just shared that processor with 20 other VMs that were all doing the same thing. This is the soundproof, unbreakable wall we were looking for. The isolation is almost perfect because the VMs don't even know their neighbors exist. They don't share a common operating system. They don't share files. They don't share memory space. They only share the underlying physical hardware, and their access to that hardware is ruthlessly policed by the hypervisor. A crash in one virtual machine has zero effect on another. A security breach in one is contained, unable to see or access the others running on the very same piece of silicon. This is the innovation that unlocked the first wave of massive cost savings in corporate America. Suddenly, a company didn't need 20 different physical servers, each running at 5% capacity. They could buy one single powerful server and run those 20 different workloads as 20 isolated virtual machines on that one box. This is a concept called server consolidation. The one server could now run at 70 or 80% capacity, which is vastly more efficient. Hardware costs plummeted. Power and cooling bills dropped through the floor. The amount of physical space needed in expensive data centers shrank dramatically. Companies like VMware built billion-dollar businesses on this revolution alone, long before the term cloud computing was even a buzzword. They enabled US companies to take the sprawling, inefficient server farms they had built in the 90s and shrink them down, saving literally millions of dollars in the process. This virtualization, powered by the hypervisor, is the bedrock technology of resource pooling. When you ask Amazon, Google, or Microsoft for a server in the cloud, you're not getting a physical machine. You're getting one of these. A virtual machine, a perfectly isolated slice of a much larger, shared physical server. It's why they can offer you computing power so cheaply and so quickly. They aren't racking a new physical server for you. They're just spinning up a new VM, a process that takes seconds instead of weeks. But this solution, as brilliant as it is, creates a new, more subtle problem. We've built soundproof walls between the apartments. The isolation is secure. But what happens when the tenant in apartment 7B decides to host a party with 1,000 people? They might not be making any noise that you can hear, but their activity is shaking the entire building's foundation. In the cloud, this is known as the noisy neighbor problem. Even if your VM is perfectly isolated, it's still sharing the real CPU, the real memory, and the real network connection with other tenants. What happens when another company's application on the same physical hardware suddenly goes viral? What happens when Netflix, running on the same server rack as a small business's website, releases a new season of a hit show and millions of people start streaming it at once? Their VMs will start demanding a massive share of the server's resources. Does that mean the small business's website suddenly slows to a crawl? Does one tenant's success inadvertently crush another tenant? If the cloud provider can't solve this, then the promise of reliable performance falls apart. The hypervisor's job, it turns out, is far more complex than just building walls. It also has to be an incredibly sophisticated traffic cop, a resource scheduler, and a fairness doctrine all rolled into one. It has to perform a constant, high-speed balancing act, ensuring every single tenant gets the performance they're paying for, regardless of what their neighbors are doing. How it pulls off this incredible feat of resource management is the next layer of genius that makes the whole system work. So, at the heart of this digital city, managing all these tenants in their high-rise apartments, is an invisible, all-powerful building superintendent. It's not a person, of course. It's a foundational piece of software, and its real name is the hypervisor. And this hypervisor is the unsung hero, the secret sauce, the absolute cornerstone of modern cloud computing. It's the ghost in the machine that makes resource pooling not just possible, but incredibly profitable. Think of it like this. The physical server, the actual box of metal, silicon, and wires, is the raw land. The hypervisor is the master architect and construction foreman that builds a virtual apartment complex on top of that land. It doesn't use bricks and mortar. It uses code to create isolated, secure virtual suites. Each of these suites is a virtual machine or a VM. To the tenant, their VM looks and feels exactly like their own private, dedicated computer. They have their own operating system, their own memory, their own storage. They can install whatever they want, run whatever they want, and they are completely oblivious to the fact that they are sharing the same physical roof, the same processor, the same memory sticks with dozens, sometimes hundreds of other tenants. The hypervisor's first and most critical job is isolation. It builds impenetrable digital walls between each VM. What happens in tenant A's apartment stays in tenant A's apartment. If their application crashes, it doesn't affect tenant B. If tenant C gets a virus, the hypervisor acts like a perfect quarantine, ensuring it can't spread to tenant D next door. This is the baseline, the absolute table stakes. Without this perfect isolation, multi-tenancy would be a chaotic and insecure nightmare. But this is where the real genius begins. The hypervisor isn't just a wall builder. It's a ruthlessly efficient resource allocator. It's constantly watching, measuring, and directing the flow of the building's core utilities, processing power, memory, and network access. And it has to solve one of the biggest challenges in any shared environment, the noisy neighbor problem. Imagine you're running a small but growing e-commerce store. It's the biggest sales day of the year. Your website is one VM, one apartment in this massive cloud server. In the apartment right next to yours is another company, let's say a data analytics firm, and they've just decided to run a massive, computationally intensive report. Their task starts demanding a huge amount of the server's processing power. It's the digital equivalent of your neighbor deciding to test a jet engine in their living room. In a poorly managed system, that jet engine would shake the whole building. The shared CPU would get bogged down by the data firm's massive task, and your e-commerce site would slow to a crawl. Your customers would see spinning wheels instead of add to cart buttons. Sales would plummet. It would be a catastrophe. But the hypervisor is there to prevent this. It acts as a traffic cop for the CPU. It has a scheduler, an incredibly sophisticated algorithm that slices time into microscopic slivers called milliseconds. And it doles out these time slices to each VM in a perfectly fair and controlled manner. Even when the data analytics firm is screaming for more power, the hypervisor steps in and says, "Hold on. You get your designated slice of time, and that's it. Then, in the very next millisecond, it pivots and gives a slice of time to your e-commerce site, and then to another tenant and another, cycling through all of them thousands of times per second. This process, often called round-robin scheduling or fair queuing, happens so blindingly fast that from the perspective of each tenant, it feels like they have the processor all to themselves. Your website remains snappy and responsive, completely shielded from the noisy neighbor next door. The hypervisor ensures that one tenant's massive workload can't starve the others. It guarantees a baseline of performance, a service-level agreement that you can count on, no matter what anyone else on the server is doing. It gets even smarter when it comes to managing memory or RAM. This is one of the most expensive and precious resources in a server. The hypervisor pulls off an amazing trick here called memory overcommit. Let's go back to the apartment building. The building has a central water tank. That's the physical RAM in the server. Let's say it holds 1,000 gallons. Now, you might have 20 tenants, and you promise each of them that they can use up to 100 gallons of water if they need it. If you do the math, that's a promise for 2,000 gallons, but you only have a 1,000-gallon tank. This sounds like a recipe for disaster, but the hypervisor is a master observer. It knows that, on average, most tenants only use a fraction of their allocated water at any given time. Tenant A might only be using 10 gallons, tenant B is using 20, and so on. The hypervisor constantly monitors this. When a new tenant, tenant C, suddenly needs a burst of 80 gallons, the hypervisor doesn't panic. It knows there's plenty of unused water sitting in the pipes of the other tenants. It intelligently and transparently borrows that unused memory from where it's not needed and gives it to where it is. It even has a technique called memory ballooning. If the system starts to run low on physical memory, the hypervisor can inflate a small balloon inside a VM that isn't using its full memory allocation. This balloon gently pushes that VM's operating system to release its unused memory pages back to the hypervisor, which can then reassign them to a VM that's under pressure. It's an elegant, non-disruptive way to reclaim wasted resources. This ability to overcommit and dynamically shuffle memory is a massive cost saver. It means a cloud provider can sell access to more virtual memory than physically exists in the server, because it knows it will never all be used at once. This dramatically increases the density of tenants on a single machine, maximizing the return on that expensive hardware. It's like a hotel being able to sell 120 room nights for a 100-room hotel, because they know statistically 20 people will be no-shows. It's a calculated, data-driven optimization that saves millions. Finally, the hypervisor manages storage and network I/O. The flow of data in and out of the server. Let's say your noisy neighbor starts downloading a gigantic dataset, threatening to saturate the server's connection to the internet. The hypervisor's I/O throttling kicks in. It places a speed limit on that one VM, ensuring that its massive download doesn't choke the connection for everyone else. Your e-commerce customers can still load pages quickly, and other tenants can still access their data, because the hypervisor is enforcing fairness on the digital highway. So you see, this hypervisor layer is not just a simple divider. It is an active, intelligent, dynamic resource manager. It's a scheduler, a memory broker, a traffic cop, and a security guard, all rolled into one incredibly complex piece of software. By performing this constant, high-speed balancing act, it allows cloud providers to pack their servers with tenants far more densely and safely than would otherwise be possible. Every CPU cycle it saves, every byte of memory it reclaims, every network packet it prioritizes, contributes to a more efficient system. And that efficiency is the engine of the cloud's economic model. It's what turns a $10,000 piece of hardware into a platform that can generate hundreds of thousands of dollars in revenue, while simultaneously providing services to businesses at a fraction of the cost of doing it themselves. It's the silent, invisible force that turns a pool of raw resources into a reliable, scalable, and affordable utility. But managing resources inside a single box is only the first step. The real magic, the kind of scale that powers global enterprises, happens when you start to pool not just the resources inside one server, but thousands of servers together. What happens when your e-commerce store doesn't just need a little more power, but needs to handle the traffic of a Super Bowl commercial? That's when we move from the scale of an apartment building to the scale of an entire city grid. This city grid isn't just one data center. It's a network of massive interconnected data centers spread across the entire country, and indeed the entire globe. And you, your startup, and Fortune 500 giants are all plugging into the same grid. This is the core principle of multi-tenancy, and it's where the real mind-bending savings begin. Think about the electricity in your home. You don't own a power plant. You don't manage a team of engineers to keep the turbines spinning or worry about the price of coal. You just plug your laptop into the wall and the power is there. The power company operates a massive, shared grid, pooling energy from hydroelectric dams, solar farms, and natural gas plants. They manage this unfathomably complex system so you don't have to. You share that grid with your neighbors, the local hospital, and the Tesla Gigafactory down the road. Everyone is a tenant on the same power grid. Cloud computing resource pooling works in exactly the same way. A single massive software and hardware infrastructure serves thousands, or even millions, of customers simultaneously. Each customer is a tenant. They all share the same underlying physical servers, storage systems, and network gear. But their digital homes, their applications, and their data are completely private, isolated, and secure. This is the billion-dollar question. How is that even possible? How can Amazon host its biggest retail competitor, Netflix, on its own servers without one seeing the other's data? The answer is a technological marvel called virtualization, and its more modern cousin, containerization. Let's break it down. Imagine one of those giant physical servers in a data center, a beast of a machine with more processing power and memory than you could ever use. In the old days, a company would buy that server and run one application on it. The problem? Most of the time, that application might only use 10% of the server's power. The other 90% is pure waste. Wasted electricity, wasted cooling, and wasted capital. It's like buying an entire 80-story skyscraper just to house your two-person accounting firm. Virtualization changes the game. A special piece of software called a hypervisor acts like a master architect for that skyscraper. It can take that single powerful physical server and digitally partition it into dozens of smaller, completely isolated virtual servers, or virtual machines VMs. Each VM acts like its own independent computer. It has its own operating system, its own dedicated slice of memory and processing power, and its own secure storage. To the software running inside it, the VM is indistinguishable from a physical machine. The tenants in VM Apartment 12B have no idea that the tenants in Apartment 47C even exist, even though they're all living inside the same physical building. This is how a cloud provider like Microsoft can have one physical server running a banking application, a video game, and a university's research database all at the same time, with each one hermetically sealed off from the others. But the industry didn't stop there. They asked, can we get even more efficient? What if, instead of building separate houses on a street, we could build individual self-contained apartments inside one hyper-efficient skyscraper? That's the idea behind containers. Instead of virtualizing the hardware, containers virtualize the operating system. This means multiple applications can share the core foundation of the building, the operating system kernel, but live in their own secure, isolated apartments. It's lighter, faster, and allows for even more density. If a VM is a single-family home, a container is a sleek, modern studio apartment. You can pack way more of them into the same city block, and you can build a new one in seconds instead of minutes. This technology, powered by tools like Docker and Kubernetes, is the engine behind most of the modern apps you use every day. So, how does all this partitioning and isolating save US companies millions? It comes down to two powerful forces: economies of scale and utilization efficiency. First, economies of scale. Amazon, Google, and Microsoft don't buy servers by the dozen, they buy them by the 100,000. They don't negotiate electricity for one building. They build their own substations and broker deals directly on the energy market. They get wholesale prices on hardware, networking, and power that no individual company could ever hope to achieve. This is the Costco model applied to the digital world. By pooling resources for millions of customers, they can pass on a portion of those massive savings. You're effectively getting access to a billion-dollar infrastructure for a monthly fee that's less than the salary of a single IT engineer. But the second reason is even more profound: utilization efficiency. That server we talked about, sitting idle 90% of the time? That's the reality for most businesses that run their own data centers. They have to build for their absolute peak demand. A retailer like Best Buy has to have enough server power to handle the crushing traffic of Black Friday. But what about a random Tuesday in April? That multi-million-dollar investment is sitting there, burning electricity and doing almost nothing. It's a colossal waste. In a pooled, multi-tenant cloud environment, that waste is practically eliminated. The cloud provider's sophisticated management software is a master chess player, constantly shifting workloads around its global grid. When Best Buy's servers are quiet at 3 a.m. Eastern Time, that underlying physical hardware isn't sleeping. It's being used by a company in London processing their end-of-day financial reports. When a gaming company in California sees a massive spike in players on a Friday night, the cloud can instantly borrow resources that were being used by East Coast businesses that have already closed for the weekend. By sharing the pool, the overall utilization of the hardware skyrockets, from a dismal 10 to 15% in a traditional data center to upwards of 70% or even 80% in the cloud. This isn't just a small improvement. It's a revolutionary leap in efficiency. It means fewer physical servers are needed to do the same amount of work, which means less energy consumed, less real estate required, and less raw material mined from the earth. The cost savings are passed directly to the customers. The retailer no longer has to build a cathedral for an Easter service. They can just rent a stadium for a few hours and then give it back. They pay for the peak, but only when the peak happens. This fundamental shift saves large US companies not just millions, but in many cases, hundreds of millions of dollars in capital expenditure and operational costs. They can turn their focus from managing hardware to what they do best: building products, serving customers, and innovating. This massive, shared city grid is incredibly efficient, but it also sounds incredibly fragile. How do cloud providers ensure that one tenant's catastrophic failure, or a simple hardware malfunction, doesn't bring down the entire city for everyone else? The answer lies in building a city that can heal itself. This self-healing city isn't a metaphor for some far-off future. It's the fundamental design principle of every major cloud provider on Earth. It's a city built not just to withstand a storm, but to expect one every single day. Imagine one of those massive data centers we talked about. A warehouse the size of a dozen football fields, filled with humming racks of servers. Let's say one of those servers, we'll call it Server 101, is running a critical piece of an online shoe store's checkout process. Suddenly, due to a microscopic flaw in a silicon chip, its processor overheats and dies. It goes completely dark. In the old world, before the cloud, this would be a catastrophe. An alarm would blare. A technician would get a frantic page at 3 in the morning, rush to the office, identify the dead machine, physically replace it, and then spend hours restoring the software from a backup. All the while, no one can buy shoes. The store is losing thousands of dollars a minute. The brand's reputation is taking a nosedive. In the self-healing cloud city, what happens is almost nothing. The moment Server 101 fails, a monitoring system, think of it as the city's nervous system, detects that its heartbeat has stopped. It was supposed to send a tiny, "I'm okay" signal every second, and for the last 2 seconds it's been silent. This isn't a suggestion of a problem, it's a declaration of death. Instantly, automatically, and without any human intervention, the system declares Server 101 dead and quarantined. The load balancer, which was previously sending a portion of the checkout traffic to Server 101, immediately strikes it from the list of healthy destinations. It's like a hyper-efficient traffic cop seeing a car wreck, and in less time than it takes you to blink, has already set up a detour, rerouting all cars to other identical open lanes. The customers checking out on the shoe store's website experience nothing, maybe a 50-millisecond delay that is completely imperceptible. Their transaction simply gets handled by Server 102 or Server 587, which are identical clones running the same software, pulling from the same pool of resources. This is the first layer of self-healing, automated failover. It's built on the principle of extreme redundancy. In a cloud data center, there isn't just one of anything important. Every server has redundant power supplies connected to different power distribution units. Every network switch has multiple uplinks. Every rack has connections to multiple core routers. The philosophy is called no single point of failure. The engineers assume that every single component will fail, and they design the system so that when it does, it doesn't matter. The city is designed with 2 hearts, 4 lungs, and a dozen kidneys. But what if the failure is bigger? What if it's not just one server, but an entire rack of them that loses power? What if a clumsy technician trips and unplugs the wrong master cable, taking a whole row of the city offline? This is where the next layer of the self-healing city kicks in: availability zones. This is one of the most brilliant, yet simple concepts in modern computing. An availability zone, or AZ, is essentially a discrete data center. It's a separate building with its own independent power, its own cooling, its own networking, its own physical security. It might be a few miles away from another AZ, but it's on a completely different floodplain and connected to a different part of the electrical grid. A cloud provider's region, like US East 1, isn't one giant building. It's a cluster of these independent availability zones, all connected by super-fast, privately owned fiber optic cables. So when a company like our shoe store deploys their application, they don't just run it in one building. The cloud makes it incredibly easy for them to run their application simultaneously across multiple AZs. They have active, running copies of their checkout system in, say, 3 different isolated buildings at the same time. Now let's replay our disaster. A water pipe bursts inside the first data center, shorting out an entire section and taking 1,000 servers offline, including the ones that were handling the shoe store's traffic. The system doesn't even flinch. The load balancers, which operate across all the AZs, simply stop sending traffic to the flooded building. The traffic that was going there is instantly redirected to the identical servers running in the other 2 dry, happy, and fully operational buildings. For the end user, for the person buying shoes, the experience is exactly the same, seamless. They have no idea that a minor biblical flood just occurred in the building that was processing their request a moment ago. The city didn't just heal a broken part. An entire district went dark, and the rest of the city picked up the slack so perfectly that none of the citizens even noticed. This architecture is what allows companies to survive events that would have been extinction level just 15 years ago. In 2012, a massive electrical storm swept through Northern Virginia, home to the largest concentration of data centers in the world. It knocked out power to one of Amazon Web Services' largest availability zones. Dozens of major websites that were solely reliant on that one AZ, like Netflix, Pinterest, and Instagram, went down. It was a wake-up call for the entire industry. But the companies that had followed the best practices, the ones that had spread their applications across multiple AZs, stayed online. The storm had taken out a whole district, but their part of the city kept running. Netflix, in fact, took this lesson so much to heart that they invented a legendary tool to enforce this resilience. It's called Chaos Monkey. Chaos Monkey is a program that they unleash inside their own live production systems. Its job? To randomly kill their own servers. On purpose. All day, every day, Chaos Monkey is roaming through Netflix as part of the Cloud City, like a tiny Godzilla, randomly shutting down servers without warning. This sounds insane. Why would you purposefully try to break your own system while millions of people are trying to watch movies? Because it forced their engineers to build a system that was immune to random failure. They had to design their software with the absolute assumption that their servers could disappear at any second. They had to build a self-healing city so robust that it could withstand constant, random internal attacks. The result? Netflix has become one of the most reliable, resilient streaming platforms in the world. They built an anti-fragile system by making failure a routine, everyday event, not a scary once-a-year emergency. And now we get to the heart of the matter. How does this all connect back to resource pooling? That shoe company could never ever afford to do this on its own. They can't build 3 of their own data centers in different states, with independent power grids, and link them with private fiber. They can't hire a team of engineers to build their own version of Chaos Monkey. The cost would be astronomical, hundreds of millions of dollars. But they don't have to. Because of resource pooling, they are tapping into a city that someone else, Amazon, Google, Microsoft, has already built. The immense pool of servers they are drawing from isn't all in one basket. It's spread across all of these resilient, self-healing structures. When they request a virtual server, they can specify that they want its backup to be in a different availability zone. The cloud provider's automation handles the rest. The redundancy, the automated failover, the load balancing, the multi-AZ architecture. These aren't expensive add-ons. They are fundamental properties of the pool itself. The cost of all this incredible resilience is shared among hundreds of thousands of tenants, making it astonishingly cheap for each one. So the smart trick of resource pooling doesn't just save companies money on hardware. It saves them from the single greatest cost of all, the cost of going dark. It gives a small startup the same disaster-proof infrastructure that was once the exclusive domain of Wall Street banks and the federal government. They are renting a tiny apartment, but it's an apartment in a city that can withstand an earthquake, automatically reroutes traffic around accidents, and has a paramedic stationed on every corner. This creates a system that is mind-bogglingly efficient and shockingly robust. But it also raises a deeply important question. If you're sharing a city with thousands of other tenants, what's to stop your neighbor's problems from becoming your own? If the city's resources are a giant shared pool, how do you keep their data out of your water supply, and your data out of theirs? What happens when one tenant in the pool becomes a noisy neighbor, consuming so many resources that it slows down the entire neighborhood for everyone else? These are the billion-dollar questions, the very problems that stood between the dream of cloud computing and the reality. The solution, when it arrived, was so elegant and so powerful that it became the bedrock of the modern internet. The answer lies in a concept called virtualization, and the unsung hero of this story is a piece of software called a hypervisor. Imagine our big, powerful server is a massive state-of-the-art apartment building. You, as a company, don't need the whole building. You just need a 2-bedroom apartment. Your competitor, that startup you're worried about, only needs a studio. Now the hypervisor is the world's most sophisticated, paranoid, and efficient building manager. Its job is to take this one giant physical building, one physical server, and digitally slice it up into hundreds of completely separate, secure, and private virtual apartments. We call these virtual machines, or VMs. Each VM is a complete, self-contained computer, just existing in software. It has its own virtual processor, its own virtual memory, its own virtual storage, and its own virtual network connection. The hypervisor creates impenetrable walls between them. To you, inside your virtual machine, it looks and feels like you have your very own dedicated server. You can't see your neighbor's apartment, you can't access their mail, and you certainly can't tap into their water supply. The hypervisor enforces this separation at the most fundamental level of the hardware. It's like having walls made of solid bedrock. A flaw in your application, or even a security breach within your own VM, is contained. It cannot escape that virtual box to affect anyone else in the building. This is how Amazon, Microsoft, and Google can have fierce competitors like Netflix and Disney, or Coke and Pepsi, running their applications on the exact same physical piece of silicon, sometimes mere inches apart, without any risk of data cross-contamination. The hypervisor is the digital peacekeeper, the ultimate enforcer of privacy. But that only solves the first problem. What about that noisy neighbor? What happens when the tenant in apartment 3B decides to run 1,000 high-powered servers for a crypto mining operation, sucking up all the building's electricity and bandwidth, and slowing everything down for everyone else? This is where the hypervisor's genius goes to the next level. It's not just a builder of walls, it's a master of resource allocation. The cloud provider, the landlord, doesn't just rent you the space. They rent you a guaranteed level of service. Your contract, your service level agreement, says you are paying for a specific amount of computing power, a certain amount of memory, and a guaranteed network speed. The hypervisor acts as the smart utility meter for the entire building. It constantly monitors every single tenant. If tenant 3B starts trying to pull more power than they're paying for, the hypervisor throttles them. It puts a cap on their consumption, ensuring that their noisy activity doesn't cause a brownout for the rest of the building. It guarantees that you will always get the resources you paid for. In fact, it's even smarter than that. Cloud providers know that most tenants don't use all of their resources all of the time. Your e-commerce site might be quiet at 3 a.m. but get slammed on Black Friday. So, they created systems for burstable performance. Think of it like this. You pay for a standard 1-lane road to your apartment, but the building manager knows the main highway is usually empty. So, if you suddenly have a huge delivery truck coming, the hypervisor can temporarily let you use 3 or 4 lanes, as long as nobody else needs them. You get a massive temporary boost in performance for free. But the moment another tenant needs their guaranteed lane, the hypervisor scales you back to what you're paying for. This dynamic, intelligent, sub-second allocation and reallocation of resources is happening millions of times a day across the globe. It's how the cloud feels both infinitely scalable and consistently reliable. It's the ultimate solution to the noisy neighbor problem, turning a potential weakness of resource pooling into a massive strength of flexible, on-demand power. This combination of bulletproof isolation and intelligent resource management is what unlocked the entire cloud economy. It's what allowed companies to confidently move their most critical data and applications into a shared environment, reaping the cost savings without sacrificing security or performance. But the story of pooling efficiency doesn't stop there. Just when the world got used to the incredible efficiency of virtual machines, an even lighter, faster, and more efficient method of pooling emerged: containers. If a virtual machine is like renting an entire self-contained apartment in the building, a container is like renting a single, perfectly furnished room in a hyper-efficient hotel. The VM has its own kitchen, bathroom, and electrical system, its own entire operating system. It's fully self-sufficient but also heavy and takes time to set up. A container, on the other hand, shares the hotel's main plumbing and electrical grid. a single, shared operating system kernel. But your room is still completely private and secure with its own lock and key. Because containers don't have to carry the weight of a full operating system, they are ridiculously lightweight and incredibly fast. You can spin up a new container in milliseconds, compared to the minutes it might take to boot up a full virtual machine. This means you can pack far more containers onto a single server than you can VMs, squeezing even more value out of the same piece of hardware. This is a level of density and efficiency that takes resource pooling to its logical extreme. You've probably heard the names associated with this revolution: Docker and Kubernetes. Think of Docker as the company that perfected the standardized, prefabricated hotel room. It provides the tools to package an application and all its dependencies into one neat, tidy, portable container. Kubernetes, originally a project from Google, is the master hotel manager. It's an orchestration platform that manages tens of thousands of these container rooms across an entire fleet of servers. It decides where to place new containers, how to handle traffic between them, and what to do if one of them fails, automatically starting up a new one to take its place. This container-based approach has become the standard for modern software development. For a company like Spotify, it means they can deploy hundreds of tiny, independent services that all work together to bring you music. When a new feature is ready, they don't have to update a giant, monolithic application. They just deploy a new version of one tiny container, causing zero downtime for the user. For a US financial institution, it means they can scale their fraud detection algorithms almost instantly during peak transaction hours by launching thousands of temporary containers, and then scale them back down to save money when the rush is over. This relentless drive for efficiency, from physical servers to virtual machines to containers, is the hidden engine of the digital world. Each layer of abstraction allows for denser pooling, greater cost savings, and more speed. It's a multi-trillion-dollar optimization problem that the brightest minds in technology have been working on for decades. They've built the digital equivalent of a global city with shared infrastructure so robust and so efficient that it can power nearly every aspect of our modern lives. We've seen how this incredible trick of pooling works, from the secure walls of the hypervisor to the lightning-fast efficiency of containers. But the truly mind-blowing part isn't just how it saves tech companies money. It's how this fundamental shift in computing is now quietly revolutionizing the most physical, real-world industries in the United States, in ways you would never ever expect. What does any of this have to do with the price of corn in Iowa, or the speed of a medical diagnosis in a Texas hospital? The answer is everything. Let's start with the price of corn in Iowa. Imagine a massive John Deere combine harvester, a 10-ton green and yellow beast, rolling through an endless field under the Heartland sun. This isn't just a machine for cutting crops anymore. It's a mobile data center. It's bristling with dozens of IoT sensors, GPS trackers, and high-resolution cameras. It's constantly measuring soil moisture, nitrogen levels, plant health, and the exact yield of every single square foot of that field. It's generating terabytes of data, not per day but per hour. Now multiply that by thousands of combines across the Midwest, all operating simultaneously during the peak of the harvest season. Where does all that data go? And more importantly, who has the raw computing power to process it in real time to make it useful? A decade ago, the answer was almost nobody. A local farming co-op certainly couldn't afford a billion-dollar server farm. But today they don't have to. That fire hose of data is beamed up to the cloud. And this is where resource pooling changes the entire economic model of American agriculture. Amazon Web Services or Microsoft Azure or Google Cloud, they have built data centers the size of small cities. They have a colossal, almost incomprehensible pool of processing power. During the spring planting season and the fall harvest, the agricultural sector's demand for this power skyrockets. The cloud provider's multi-tenant architecture sees this spike and dynamically allocates a massive slice of its pooled resources. Its virtual machines, its storage, its specialized AI processors, to analyzing that farm data. Algorithms churn through the information, creating hyper-detailed maps that tell a farmer, this corner of your field needs 8% less fertilizer, or the soil over here is too dry, adjust your irrigation. This is precision agriculture. It means less waste, lower fuel consumption for the tractors, higher crop yields, and ultimately, a more stable and affordable price for that corn. When harvest season is over, and the demand plummets, those same computing resources are instantly reallocated from the pool to serve another industry hitting its peak. Maybe it's a retailer handling the Black Friday rush, or a tax prep software company in April. The farmer only paid for the exact slice of supercomputing power they needed, for the exact few weeks they needed it. They rented a fraction of a skyscraper's worth of power instead of being forced to build one themselves. That is the power of the pool. Now let's fly down to a sprawling hospital campus in Houston, Texas. A patient is rushed into the emergency room and sent for an urgent CT scan. The resulting images are gigantic, incredibly detailed 3D models of the human body. Finding a tiny life-threatening anomaly in that sea of data is like finding a single specific grain of sand on a beach. It takes a highly trained radiologist's time, and time is the one thing this patient may not have. But now, that CT scan is also uploaded to a secure HIPAA-compliant cloud. In that same instant, an artificial intelligence model, trained on millions of previous scans, begins its own analysis. Running this kind of AI requires a very specific, very expensive type of hardware, GPUs or graphics processing units. The same chips that render video games are miraculously good at spotting patterns in medical images. But a single hospital, even a large one, can't justify buying 1,000 of these high-end GPUs that would sit idle 95% of the time. They don't have to. The cloud provider has a massive pool of these GPUs. The moment that scan hits the cloud, the system's load balancer says, "I need 200 GPUs for the next 90 seconds. It instantly carves out that power from the shared pool, gives it to the hospital's AI, and the analysis is done. The AI highlights 3 suspicious areas for the human radiologist to review immediately. The diagnosis time is cut from hours to minutes. The patient is rushed into surgery. A life is saved. Once the analysis is complete, those 200 GPUs are released back into the pool, ready for the next task. Maybe it's a Hollywood studio in California needing to render a scene for a blockbuster movie, or a car company in Detroit running a complex physics simulation for a new electric vehicle. The hospital, the movie studio, and the car company are all sharing the same fundamental resource, using it only when they need it, and paying only for what they use. This makes life-saving, cutting-edge medical technology accessible and affordable to regional hospitals, not just elite research institutions. It accelerates medical breakthroughs. It directly impacts the speed and quality of care you or your family might receive. So what does this all mean? It means this seemingly abstract IT concept is one of the most powerful economic forces of the 21st century. Resource pooling isn't just about saving a tech company a few bucks on their server bill. It is a fundamental democratization of power. It gives a 2-person startup in a garage in Boise, Idaho, access to the same level of raw computing infrastructure as a Fortune 500 behemoth. It allows a family farm in Nebraska to leverage the same AI and data analytics as a multinational agricultural corporation. It lets a community hospital in rural Montana offer a level of diagnostic speed that was once the exclusive domain of the Mayo Clinic. This is the quiet revolution happening behind the screens. It's the digital equivalent of the national power grid. You don't have to build your own power plant to turn on a light. You just plug into the wall. You tap into a massive shared pool of electricity. Cloud computing has done the same thing for intelligence, for processing, for digital capability. It has turned supercomputing into a utility. The next time you stream a movie on Netflix without it buffering, you're seeing resource pooling in action, balancing the load of millions of users. The next time you see a self-driving car navigating a complex street, you are seeing the result of AI models trained on massive pooled computing resources. The next time you buy groceries and the price seems stable despite supply chain disruptions, you are feeling the downstream effects of logistics companies using pooled data analytics to optimize their routes in real time. This isn't just a smart trick. It's a paradigm shift. It is the invisible engine driving American innovation, making our most critical industries, from agriculture to healthcare to manufacturing, leaner, faster, and smarter. It allows us to solve bigger problems, to analyze more complex data, and to build a future that would have been unimaginable just 20 years ago. It's a story about sharing, about efficiency, and about how the simple, elegant idea of not letting a single transistor go to waste is quietly saving companies millions, and in the process changing everything. The true power isn't in owning the resource, it's in having access to the pool.